Hello classmate, in this class we will learn about sequential logic circuits. Digital circuits are widely used in automotive circuits. Electronic control unit is a typical digital system. Sequential logic is an important part of digital circuits. Understanding the basic concepts of sequential logic and master the analysis method of sequential logic for understanding and analyzing automotive digital. In this class, we will learn the concept of sequential logic circuits and basic analysis methods. A sequential logic circuit refers to any. The steady-state output not only depends on the input signal at that moment, but also depends on the original state of the circuit. This is the definition of a sequential logic. It is also the logic function that distinguish and characterize other circuits such as counters, memories, shift registers, and latches are typical devices of sequential circuits. So what are the specific functions? We need to master its basic analysis methods. Take the sequential logic circuit shown in the figure. As an example, we discuss its analysis methods and steps. The first step is to analyze the circuit type. In a sequential logic circuit, if there are no other input signals except the CP clock pulse, it belongs to the mode type. If there are other input signals, it is a mini type. The clock pulses of each flip-flop share the same CP pulse. It is called a synchronous sequential logic circuit. If not using the same CP as the path trigger, it is called asynchronous sequential logic circuit. Obviously, this counter circuit is a mod type. It is asynchronous sequential logic circuit. The second step is to write down the corresponding equations. For the above mod type circuit, we only need to write the clock equation, the driving equation, the next state equation, the driving equation, next state equation, and the clock equation as shown in the figure. The third step is to draw the timing waveform diagram. Stage transition. Choose stable or stage transition diagram. Substitute the driving equation into the next. We get an equation plus E equals Q 0 N 9Q1 加1 equals Q1 9 non-Q2n equals Q2n on Q1n. The counter needs to be cleared before counting. Start counting when all three flip-flops are in state 0. From the derived next state equation, every time each flip-flop counts, the path state will be flipped once. Its working condition can be described by a timing waveform as follows when the clock pulse signal. CPU waveform is as shown in the figure. The waveforms of Q0, Q1, and Q2 are as follows. When the clock signal CP changes from E to 0, the state of Q0 is flipped. That is, when the current state is 0, the next state is E. When the current state is E, the next state is 0. Q0 forms such a waveform. Whenever the Q0 signal changes from E to 0, the state of QE is flipped. QE forms such a waveform. Whenever the QE signal changes from E to 0, the state of QR is reversed. QR forms such a waveform. The counting starts from 3-bit binary no 000 to E, and then starts counting from 0 again for a total of bar completing a cycle. So it is called a modular bar counter. Then according to the timing waveform, we can list the truth table of state transition. The truth table of state transition is shown in the figure. It is the timing waveform by the state transition truth table. Also reflect that the counter starts from state 0 to start counting. Every time a counting path count, the binary value increases by E. When the S path is inputted, counts to 0. As a whole, the circuit can be called a module bar up counter or oct counter. Make a state transition diagram as shown in the figure. QRN, QEN, and QLN represent the output numbers. Indicates the order of the trigger output numbers. From the state transition diagram, we can intuitively see the order and modulus of the counter's counting. Due to the 8 binary numbers in the counter's loop body are all combinations of the 3 flip-flop outputs. Therefore, when it starts without being cleared, it can also from any state enter the valid cycle. We call this ability to automatically enter the effective loop as self-starting ability. If after the counter is started, the state cannot enter the valid cycle by itself, it is called not having self-starting ability. From the above example, we can summarize the general analysis steps of sequential logic circuits. First, determine the type of sequential logic circuit. Second, write down the corresponding equations of the known circuit. Third, draw timing waveform diagram. Stage transition to stable or stage transition diagram. Fourth, identify the function of the sequential logic circuit. Nowadays, most cars manipulation and control functions are all digital circuits. As engine operating condition control systems, the anti-lock braking system, electronic suspension system, electronic power conversion, and management control systems, mastering the analysis methods of sequential logic circuit, automotive fault diagnosis and repair. In this course, we learned the definition of sequential logic circuits and its basic analysis methods and steps. Let's test our learning results. Please analyze the timing logic circuit shown in the figure and write its functional truth table. The truth table of the timing circuit is as follows. Did you analyze it correctly?